Okay, I assume everybody can hear me, and
Yes,
thank you.
we hear you.
Right, thank you for the introduction. I'm going to talk a little bit about LIGO and then about our individual use case. And then after I get done with the interesting stuff, I'm going to go off in the weeds on how to make complicated DAGs. If I can get my... Okay, so LIGO is, you probably heard already, but it's a large interferometer with 4 kilometer arms. And we're looking for a change in length of these arms on the order of 10 to the minus 18th meters as a gravitational wave passes through. It's the difference between the length of the two, the ratio of the length of the two, that defines strain, which is what we use to identify gravitational waves. And I saw this really cool analogy on what kind of precision we need. So if we were to look at the distance between our sun and Alpha Centauri, we're looking for a change in that difference on the order of the width of a human hair. The interferometer uses a closed loop control system, and strain is calculated from the control signals at 16 kilohertz with a nominal 5-second latency for the filters to settle. So that gives us one channel. There are on the order of 500,000 auxiliary channels that we acquire in real time. We acquire or calculate in real time at the observatories, and they are used to operate the interferometer, to monitor the health. And a big part of our whole job is to eliminate all of the other possible sources of strain channel artifacts that are not due to gravitational wave. So this case study is concerned with 1,000 channels that are used by the detector characterization group to estimate the noise and support the noise source investigations and mitigation. We use a program called Omicron, which is a C++ implementation of the Q transform. This is a multi-resolution time frequency analysis that combines Fourier and wavelet decomposition to give us good time and frequency resolution. It can produce images, but the way we use it is to generate triggers, which are short duration excess power in a particular part. So in the upper left, we see the image produced by the Q transform for the gravitational wave we detected on 14 August 2017. These were 2 black holes. One was 30 and the other 25 solar masses by our estimation. And it was about 540 megaparsecs away. In the bottom left, we see the unclustered Omicron triggers, and in the bottom right, all those get reduced to a single trigger. Okay, that was the fun part. The problem is we process these 1,000 channels at 2 observatories every 5 minutes. Some of those analyses depend on the state of the detector, some do not. So if we have a complete day of observing, we generate about 250,000 jobs. This is enough to make sure that Murphy proves himself every single day. Jobs fail for many reasons, the most common of which is a delayed arrival of data. And while this doesn't reduce our effort to find the cause of failures and mitigate them, this project says we are going to have failures. How do we go back and clean up for them? That's what makes it so nebulous what exactly each job is going to do. So we have what we call the gap filler jobs. It determines when we have data available, when the detector is in appropriate state, and when we have no triggers where there should be triggers. Then we generate a Condor DAG to fill each gap, and we can submit up to N DAGs at a time to limit our resource requests. No, we run this gap filler every day. We can run it manually for a few hours, or we can run it for a few months before we go through long-term data analysis. Okay, this is a very busy slide. I should have put it later, but basically our gap filler DAG has 3 stages. We have the find gaps, and that generates a bunch of filler jobs, and each one of those filler jobs generates a DAG, and then we have a postscript that turns that we have a postscript that modifies the original DAG to allow it to run as many of them as we want, as many as we specify in parallel. And then each one of these individual DAGs then breaks the job down into a fixed number of channels for a fixed time period, runs those. This is kind of a map reduce pattern, then merges all the adjacent files, puts them in an archive, and deletes all the intermediate files. Okay, this is an animation of how this all works. And it's used for other things. So rather than get into details on what individual lines mean, the top set of data talks about when our frame files, when our data files are available. Then the second set is looking at individual detector states. In both of these, green means they're in a good state. For example, this is the, excuse me, this is the state we want to process. This is the data we have available. Here we have missing data. And then in the bottom is our individual trigger groups. So we have, as you see, problems here. In this case, red means we should have triggers, but we don't. Green means we should have triggers and we do. And white means either data or detector state is there. So during the day, we have lots of red, and I'm not sure exactly what the problem was. But then the filler job runs and fills in all of those things, and it becomes green. And I didn't have to look too hard to find one where at the end of it, it all turns green. But that doesn't happen every day. Okay, so let's now get into the weeds on how this is actually done. The original DAG is very simple. It has a find job, a fill job, a postscript to create the subdags, and then a placeholder for where all the subdags are going to go. So find finds the gaps, fill then creates the DAG for each gap, and so on. So let's look at some submit files. So this is the DAG submit file, and just a simple find job, fill job. The postscript, I really should have not had bothered you with the parameters, but it runs Omicron subdag creates, and then it runs oh, there shouldn't be a space here, and then it runs the subdag.dag that was in the original, that is a placeholder when we created it. And then the parent-child relationships are easy. Find has to complete to run fill, and fill has to complete to run the subdags. Now, and find is very straightforward. Just define the executable, the arguments, and queue that one job. Fill is a little bit different in that the find script has a parameter on how many fill scripts it will create. And using this cool variation of the queue statement, it goes out and it finds all of the shell scripts that match this globbing pattern and runs each one. The argument is the script that it found, and it creates a unique log and error and output file for each one. The top level DAG defines a placeholder. It's all Omicron subdags, but it doesn't even create that file. When we first submit the top level DAG, that does not exist. It's the postscript Omicron subdag create that finds all the DAGs that the fill jobs created, and then it creates the subdag.dag. The subdag.dag file just uses the subdag external to list all of the DAGs, and then it uses this incantation, which Cole just taught me, to limit how many of those DAGs run at a time. Now, each one of those DAGs can end up with maybe 1,000 jobs, anywhere between 1 and 1,000 jobs to run. There's one other thing that is worth mentioning. The Omicron process itself will process about 80 to 90% of its input data using 1 gigabyte of memory. But as the noise increases and the number of triggers increases, that grows. And I don't know what an upper limit is, but when it gets to 7 gigabytes of memory, we just declare the data is to be so noisy that nobody cares. So this is how we do that. We define an initial memory request. I'm debating whether I should explain why there's no units on this one. I will leave that as a difference between the submit language and the class add language. But we cannot put a unit on this. And then our request memory looks like this. If we start out and memory usage is undefined, then request that initial request. If we run this request memory line again, and we do know that there is a memory unit, we just double it. And then we release the job for various reasons. And I think it's 34 that says it's on hold because memory usage was exceeded. And we had to add this little pause in there that says, stay in hold for at least 5 seconds. And that was, there seemed to be some kind of race condition between the job getting released before the memory got updated. And then we remove the job completely if it's idle and memory usage is more than 7 gigs. And these jobs usually complete in less than 15, 20 minutes, but if they take longer than 3 hours, something else is going on. Oh, I forgot I had this slide where I went through all of the details I just said. But anyway, 34 is memory usage exceeded. If the thing goes on periodic hold, we can release it. And if the job's duration is exceeded, then the periodic remove should take over. All right, so what do I want to say? The Condor submit language is very is very powerful, and that makes it very hard to know what you can do. I learned all of this from Cole. He's a great resource, and he answers every email that I've seen on the Condor users list. Dynamic DAGs have been great for us because we automate tasks that are data dependent, that we have no idea what they're going to do when we run them. The gap filler sometimes doesn't do anything. The find job says there's no gaps I can fill. I think that's happened. It's only been running for 3 years. And managing resource requests not only helps others, but it also helps our jobs to match more quickly and run efficiently. And then if you want to read about it, everybody is a critic. If you want to read about any of the scientific things, I included some links at the end. Thank you for your attention. I will try and answer any questions.